And so we will be recording this session. So if anybody has any objections with the recording, please say so now. Okay, thank you. So the next topic we're going to be talking about in our unit 2, still going through the design part of the of the process of creating an information system for the database, has to do with normalization. Normalization. Um, and we're going to be talking about that. You guys already did some research about that last class, so we're not going to be starting from zero, but we're going to go through the material. Normalization isn't. I don't find the topic to be very fun. Actually, I'm going to be very frank with you. I do not like. I'm not a fan of this topic, and I remember when I took my databases class, I was not a fan of this topic, and we're actually just going to scratch the surface of the topic of normalization. We could have half a course or one complete course just about databases and to talk about normalization. There's a lot of stuff relating to that. So we're just going to scratch the surface about it, just so you know what it's about and how some general rules of normalization and why they're important. And so what is normalization? Okay, so we have already gone through the process where we identify our entities, we identify our attributes, we define cardinality, we identify our primary keys, we do our ER diagram, and then from that, remember that we create our relational model, okay? And remember that the relational model are going to be, in the end, the tables, the set of tables that contain the structure for the different entities with the attributes, as well as the relationships in cardinality. And that structure defined by the relational model that's defined in these tables is basically what we're going to take and we're going to be implementing in our database software. So that part, the relational model, the tables themselves are hugely important because that's what we're going to be implementing in our database. And so thing is, we need those tables to be very well structured, or rather, we need those tables to be correctly structured. Because if these tables don't follow certain rules, some rules, as we're going to see at the beginning, are very, very basic. Other rules are a bit more complicated, might be a little bit more complicated to understand, but we need the tables to follow certain rules. And why do we need those tables to follow the rules? Because in the end, we want the structure of our database to be solid, to be congruent, so as to avoid as much as possible any sort of anomaly that could occur with the information that we're storing there, the data that we're storing there. And so any part of the structure of our tables that does not satisfy with certain rules has to be corrected. And so basically what we're going to be doing is, in this section of normalization, is that we're going to be looking at the tables. And we're going to be analyzing the tables and seeing if the tables are structured correctly. And if we need to modify anything in the tables to have this congruency. So basically, this is called normalization. And the normalization process is basically taking an entity or a table or a relationship, analyzing it and eliminating any conflicts that occur or that might be in the table or the relationship that might affect the data or the information that's stored there. And the end goal is to have our tables structured well enough for them to be congruent to guarantee that we don't have anomalies. And remember that there's basically 3 types of anomalies. We'd already talked about that with the data that we're storing and the information we're trying to extract. And these are the updating anomalies, where I modify something, the inserting anomalies, when I add something, add a new record, or add something to the structure of a database or our data. And deleting, when I remove any sort of information from the structure that we have. And the idea with normalization is for us to try to avoid these anomalies or to guarantee that these won't occur. So for example, we've got a table here. It's a typical table, the one we've been talking about. This is a table that has to do with employees, okay? Has to do with employees. Let's do a refresher here, because remember that these are going to be questions in the exam. This is a table. How many attributes does this table have? Can somebody tell me?
4.
4, correct, yes, Ali. Very well done. How many records does this table have?
5.
No, not 5.
4.
20.
4. Oh no, yes, 4.
4, correct. The first one is the header that's got the attributes. How many fields does this table have?
4.
4. Remember that there are concepts that are equivalent when we're talking about the ER modeling and the relational model. So we're talking about attributes and fields are the same thing. How many tuples does this table have?
4.
Or remember that tuples and records are the same thing. They're the rows. So this table also has 4 rows. Those are going to be questions in the exam. Remember. Now, remember that we had talked about primary keys. Let's look at the attributes or the fields that this table has. There's a field named employee here, employee ID. Then there's the employee name. Then there's the city where I imagine the employee lives. And then there's the department that the employee is a part of, right? What would maybe be an attribute that we might identify and say, well, this would probably be the best primary key for this table?
The employee ID.
The employee ID, correct. Why? Because it's something that, at least from what we're seeing here, should be something that uniquely identifies each of the employees. Okay. There's a problem with how this table is structured. There's a problem with this table, how it's structured, that can generate anomalies. Let's imagine that this is the only table we have in our database that has the employees and the departments. What do you notice? Look at the table. What's something odd that you might notice here with the data that's stored in the table? Anybody?
That in one department there are 2 values together.
Correct, and yeah, very good observation. So for example, here, the person, he, they, them, I don't know if it's a he or a she, Amit Kolhapur is assigned to 2 departments. You see that? That's that might be problematic because this person is assigned to 2 departments. Remember, this is the only data we have. Only data we have. We've got 2 departments here. What happens if I delete Amit Kolhapur from our database? I delete them completely. What's something that might be a problem here if I delete them?
I think you would lose the department, the first one.
Yes, very good observation. I think it was Carmina, right?
Yes.
Yeah, correct. Very good observation, Carmina. Right now, before I do the deletion, how many departments are identified here in the table? How many departments do I have at least here in the table?
4.
Or I've got OB, I've got Cognos, I've got SIBO, and I've got ETL. There's 4 departments that exist right now in the table. Thing is, if I eliminate, the thing is that the OBIEE department right now is only, the only person right now of these 4 that is in that department is Amit Kolhapur. So if I eliminate Amit Kolhapur, I'm totally losing this department. There's no way where I can reference it. There is no way where I can reference that department. Okay, you notice that? There's a problem there. That's a problem. That's a deletion anomaly. What's another problem that we've got in this database? Look at the information there. What's another thing that's not correct in this database? I'm sorry, in this table. Look at the table, and what you identified right now with the departments is correct. Very well done, Carmina. But what else do you notice there that's a problem in the data that we've got there?
That is I don't know how to say it. Está abreviado. Abbreviation. No?
Oh, the abbreviations of the departments, you mean, Carmina?
Yeah, but I don't think so.
No, not necessarily. We can use abbreviations. That's not necessarily a problem. But look at the information again. Oh, the data that's there. Is there?
Maybe it can be the name.
Did you already say the Amit twice?
No, Juan Ignacio. That's actually what I'm talking about. Amit Kolhapur is repeated. Do you notice that?
Yeah.
Amit. Yep, that's correct, Juan Ignacio. Amit Kolhapur is repeated in the database. Why is he or she repeated in the database? Or what's the problem with Amit Kolhapur being repeated in the database if we're using employee ID as the primary key?
He has 2 IDs.
The person has 2 IDs. That's going to be a problem because who is Amit Kolhapur? Are they employee ID 101 or are they employee ID 104? So this employee ID that we've got, this is an insertion anomaly. Somebody added something here to the database and didn't, it wasn't validated with regards to a primary key. So this is a problem. And the other thing is that it's weird because it seems like this is a different person, right? Because Amit Kolhapur 101 belongs to department OB, IEE, and Cognos, but Amit Kolhapur 104 belongs to ETL. So this is a problem. Lastly, you guys mentioned or identified that we've got 1, 2, 3. So that last one that I mentioned, that's an insertion anomaly. I'm adding something that is incongruent with the rest of the data in the database. I've got 4 departments. 1, 2, 3, 4. What if I create a new department that doesn't have any of these employees assigned to it? I'm going to add another department that's called SOSA. Well, I can't include that department I can't update this department into the database because none of these employees are assigned to this department. So where do I put it? You see that? That's an updating anomaly. Okay. Questions up to this point. What I want you guys to see is that this table, the way it's structured, even though we looked at it and say, well, we identify the fields, we see there's 4 records, we see something that can be the primary key. This table isn't correctly structured because there can be anomalies. And what we want is we want to eliminate the possibility of anomalies in the table. So this table doesn't have a structure that would be the best structure to implement in our database. We need to modify something. We need to modify a few things in this table to not have the anomalies that we just identified. However, let's try to do this with some rules, okay? And that's where normalization comes in, okay? Okay, questions up to this point? Okay, let's move on. So these are the anomalies that we're talking about. Remember these anomalies. These are. I'm going to ask you about these anomalies. So we've got updating anomalies. Any sort of update that we want to do on this table, okay? If we want to update a city, for example, that was another one, a city. We've got people, we've only got 3 cities. We didn't mention that. We've only got 3 cities. If we would, same as the department, if we were to want to add 1, 2, 3, we've got 3 cities. If we wanted to add a new city, and none of these employees were from that city, we couldn't add it because we wouldn't have a record to relate it to. The data will be inconsistent. Same thing happens with the departments. Which has to do with the insertion anomaly. If a new employee joined the company, oh, that's another thing. Let's assume that we have a new employee, but the other way around, the employee doesn't have a department assigned, then the field in the department is going to be blank. And we don't want that. We don't want null values. And what we mentioned, if we delete one of the employees that's that's assigned to a department that nobody else has, that department, that data, that information, because in the end, that's going to be information I want to process, is going to be lost, okay? This is what we want to avoid. And normalization is going to help us with that. Okay. And so what we're going to do is that we want a database that's normalized, a normalized database, okay? When we are going to do normalization, basically we're trying to validate 4 things. We want data to be organized in logical groups. We want to minimize the possibility of duplicate data. So we don't want this. We don't want duplicate data. We don't want Amit Kolhapur to appear many times if I can avoid it. Because remember that if I have duplicate data, I can have redundancies, inconsistencies, and also the database gets larger. We want the data to be organized so that when we do a modification, the modification should only be done in one place. Meaning, if I want to update, let's say that now the Cognos department is not going to be named Cognos. It's going to be named differently. I want to be able to update that name of the department just in one place. I don't want to have to update it everywhere. The other thing is that, let's say that I reassign somebody to, or people to other departments, I want to be able to do that very directly without having to structure or redefine the information that I have in the table or the database. And by the way, remember that right now we're just looking at one table, but our database can have many tables. Now imagine the problems that we identified with this table, now multiply them by 4, 5, 6, 10, or whatever, then the problem is more severe and it grows. The idea also is for the information and for the data to be organized in a way that we can access it and manipulate it quickly and efficiently. So those are basically the 4 reasons to do normalization or to do this procedure with the tables. It's also used to verify the structure of an entity. Because remember that in the exercises we've been doing, I asked you guys to identify entities for different exercises, different problems. and you defined your attributes the best way you knew how. But normalization helps us do a kind of like a double, triple check of that and say, okay, you know what? Yeah, I considered that this was going to be the primary key, but since I have these other attributes, that's not the best primary key. I'm going to have to need maybe a combination of primary keys to be able to do that efficiently. It's also a formal framework to be able to analyze and validate relational schemes. So when we get to the tables, it's a formal way of validating them before we implement them into the database. And there's something that's going to be called functional dependencies between the attributes or fields that we're going to talk about. And it's also a way to simplify. So instead of one thing that's, I don't know if any of you have faced or are going to face this situation, but I remember that last semester, no, a couple of semesters back, one of the projects by one of the students, Bruno, remember, he used to work, he's from Brazil. He used to work for a company that had to do with oil, organizing the data and the information. I remember he brought an example where all of the data was in this huge Excel worksheet. So imagine that all of the data is just stored in one huge Excel sheet, and there's hundreds of records. And there's only one huge table where all of our data is there. That's really not very practical. It's even dangerous to have your information that way, because having it that way is you're probably going to have any of the three anomalies that we mentioned. And so it's a way to do a simplification in which instead of having one huge table or a few entities, we're actually going to separate them into smaller tables that have the information organized in a certain very concrete way. And that are more simple and more easy to manipulate. So there are 6 reasons we're going to be doing normalization, complemented with the 4 important points that we already mentioned. The first one is to structure data in a way that represents the pertinent relationships between them. Remember that we identify relationships. Relationships are important. If our data doesn't have relationships or our entities aren't related, then the information system and what we store in the information system is not going to be very useful. Also, as we mentioned, to allow simple retrieval of data in response to query requests and reports. Because in the end, remember that what we want to generate is information. How do we generate information? We've got the data in the database organized in many tables, and we want to be able to do queries where we ask for specific information. I want to know all of the employees that are from department Cognos. I want to know all of the employees that live in Kolhapur. By the way, if I do that right now with this table, I'm going to have 2 records that give me the same person. It's going to be redundant. And imagine if you're printing them out, this would print 2 pages instead of 1. You don't want that. To simplify the maintenance, the updating, inserting, and eliminating, which is basically the maintenance of a database, we want to simplify that maintenance. This is a typical problem always in systems design. We design the system under certain conditions. Okay, remember the COVID-19 vaccination example that we've been doing right now? Let's say that there's a new strain of the virus that requires a 3rd vaccination. Right now, there's 2 vaccinations. And we designed our process for 2 vaccinations, a registry for 2 vaccinations. And so now we add something else, which is the 3rd vaccination process. Our system needs to be designed in a way that we can restructure and reorganize things when new requirements arise. without having to redo the whole database or a whole system. And this is a typical engineering systems problem. So you've got a system that you designed a certain way, and the system is robust. However, if new things arise and we want to modify the system or change or add things, we're basically stuck because the system is so rigid that we end up patching things. Okay, we end up patching things. I don't know how many of you are familiar with the concept of patching in information systems. I don't remember I don't remember how cool or not cool you guys are, but are there people here who play video games?
Yeah, that's what I was gonna say, Professor. That there's usually patch notes whenever they want to update a video game.
Yeah, the patch notes. What happens, and this is typical, what happens when you launch a video game and it's rushed? People start playing it and there's problems. There's a bunch of problems and people get mad. What happens there? Probably the developer wanted to get the game out, and what happens? Problems start to arise. How do you detect problems? You detect usually problems when you're using it. So think about this. When we're designing our systems, think of any of the problems that we've seen in class up to this point: the COVID-19 registration, the Netflix system, the homeowners, the city development system, the calendar programs, all of the ones that we've seen, Sosa Corp. We designed them under certain premises. And we're trying to validate everything in the design. But what's going to happen once you launch the system and users start to use the system, then problems come up. And usually a lot of problems come up if there were a lot of things that weren't considered in the previous design and testing phases. And what happens there? You need to patch things. So I don't know how many of you have been, if you play video games and you've been really stressed out because you're playing the video game, you get to a certain point, or you're doing online or multiplayer or whatever, and it crashes, or it takes away points or stuff that you've gained or whatever, and you get really mad. And a lot of people start getting mad, and suddenly the developer comes up with a patch, and the patch fixes certain things. Well, you usually have to do patchwork when your design isn't, when you didn't consider certain things in it. I don't want to say it's a bad design, but what happens is that maybe you didn't consider things in the design, you didn't consider things in the deployment, and you didn't consider things in the testing. And so instead of needing to restructure when new requirements arise, we want to consider these from the beginning and not have to do a bunch of patches in the end. We want to eliminate redundancy. So here we've got redundancy. We've got redundancy in the information in Mr. Amit I've been saying Amit Kolhapur, and I've been using the city as a second name. I'm really sorry about that. This is the city. It's Amit is the name. Amit, Vidya, Yothini, and Amit. Amit is being repeated. I was using the city as a second name. I'm sorry about that. The last name. There's redundancy here in the information because things are repeated, and we don't want that. And in the end, we want information to have integrity, or we want our data and the information to be extracted to have integrity. Why? Because in the end, why do we need information? We need it to make decisions. So if the reports, queries that we're generating generate information without integrity or trash, then the decisions we're going to be making are going to be based on trash, and we don't want that. Now, let's talk about the process of normalization. Now, normalization is based on something that's called a functional dependency. And a functional dependency has to do with the primary keys. And what is a functional dependency? It's the relationship that exists between two or more attributes. And a way of representing it is that one attribute depends on the other, or to be able to find the value of one attribute, you can use the other attribute to find it. And so this is very clear when we're talking about primary keys. So if employee ID were the primary key, then I can find any of the other attribute values for a specific instance if I access the primary key, which is employee ID. Now, that's what's called a functional dependency. It means that the rest of the attributes depend on one attribute, one or more attributes, and usually that's the primary key. That's called a functional dependency. One attribute, the values of one attribute are going to depend on the other, or as it says there it's written there, if you provide the value of one attribute, you may obtain or seek the value of the other. Okay, so that's a functional dependency. So normalization is based on that. Y is dependent on X if X determines the value of Y. Now, let's talk a little bit about the normalization forms. And so normalization forms are going to be the different stages we're going to be using to validate the information. I'm sorry, to validate the tables or normalize the tables. And it's an incremental process. So these are called normal forms. So there's the first normal form, the second normal form, the third normal form, fourth, fifth. There's a whole bunch of normal forms, the Boyce-Codd normal forms. And these are incremental. So we do the first one, we validate that. Then we go to the second one, the third one. If we go to the nth normal form, it means that all of the previous normal forms or normalization steps have been validated. So it's incremental. We're actually just going to see the first three normal forms here in the course. There's many other normal forms or normalization forms if we want to be very, 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 very strict about it. But we're not going to focus on the rest here in the course because it would actually take too much time and wouldn't serve the purpose of what we need to understand and know for this course. And you'll probably get really, really stressed about it. So let's start talking about the normal forms. The first normal form is called 1NF. The way we determine the normal forms is that in the normalization steps, that's going to be the number and then NF, which means normal form. And what is the first normal form, or what characteristics does the first normal form have? First off, all of the attributes or all of the fields can only include atomic values. That means these are values that are simple and indivisible. Okay? Simple and indivisible, meaning that anything that is going to be stored in any of the fields for a specific record, that's going to be a value that I'm not going to be able to separate into 2, 3, or more different values. Let's go back over here to the employee table that we had here. This is an example of a field or an attribute that does not comply with the first normal form. And why is that? Because we don't have atomic values for all of the elements in that for that field or attribute. And what do I mean by that? I mean that here, how many values do we have here?
2.
2. So it's either OBIE or Cognos. How many do I have here? I have 1. I have 1. And here I have 1. But here I have 2. I can't differentiate because I've got 2 of them in the same. I have 2 things that are of the same category in the same record in the same field. This cannot happen in the first normal form because this generates an anomaly. So this is an example of something that is not an atomic value. Now, the rest of the things we have here, these are atomic values. Can I separate 101 into something else, into more things? Or is that one thing or is it many things? It's one thing, right? The employee name, it's one thing. I can't separate it into more values. The city, it's one thing. I can't separate it into more values. These are atomic values. So the first rule for the first normalization is that we need to validate that in the fields and the attributes that we can only store atomic values. So if a table doesn't have atomic values stored in them, then it's not in the first normal form. So that's one thing that we need to validate. Okay. Okay, so the first rule for the first normalization or first normal form is that all of the attributes have to have atomic values. Okay, simple and indivisible. The other three are really, really common sense. Okay, if we don't follow the other three, I mean, really, really, it's common sense. The other three. Number two is that all values in a field have to be of the same type. That should be congruent. And actually, when we implement it in the database software, we're going to have to define the type of data that we use for each of the attributes. We can't combine them. So what does that mean? It means that if employee ID is going to be 101, 102, 103, 104, these have to be, this is going to be a number. So it's not valid that suddenly I say that a new employee is going to be S45, for example, or a new employee is going to be named Sols, the employee ID is going to be Solsan, for example, or something like that. If, for example, let's assume that we had another attribute here that was the birth date, then this would have to have a format that would be a date format. So I don't know, 375. Okay. And so if I suddenly wrote here, hello, or I suddenly put a 50 here, these would be incorrect. They have to be of the same data type, what we're putting in the values. That's, again, that's common sense. The other thing that's common sense is that each column or each field has to have its own name. That's also common sense. I mean, each of the four fields that we've got here have to have their own name. Employee ID, employee name, city, department. If this, if I suddenly call this city, also, then I'd have two fields of the same name, and that would be not only wrong, but it would be confusing. So it's common sense. You guys did that when you define your entities, when you define your attributes. I think there was one team where I made the observation when you define the names of the attributes that I think you'd said ID, 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 and I just said we need to put a unique attribute or identifier there. And that just means that each of the attributes or fields has to have a unique name. It shouldn't be repeated. And this is something very important in a database. The order of the columns doesn't matter. It really doesn't matter. So here, for example, we usually think, okay, the primary key has to be here on the right, then the name, then the city. We mentally put a certain order in the columns, but really the columns could be mixed up. That shouldn't be a problem. Okay, so the columns don't have any sort of order the fields. And something very, very important for the first normal form, there has to be a primary key. There has to be a primary key. If we don't have a primary key, we're in serious trouble. We need to have a primary key. These are the rules that define that our table is in the first normal form. So if we comply with these 4 rules and have a primary key, then check. Our table is in a normal form. Okay. Let's switch over here and let's watch a video. Let's watch a very short video that talks about the first normal form. Just verify that it's being opened and share.
Hello everyone, welcome back to studytonight.com. In our last video, we studied about the basic concept of normalization. We saw and understood how data redundancy can lead to several issues and how normalization can reduce data redundancy and make the data more meaningful. In this video, we will learn about the first normal form, which is like the step 1 of the normalization process. The first normal form expects you to design your table in such a way that it can easily be extended and it is easier for you to retrieve data from it whenever required. If a table or a database is not even in first normal form, it is considered as bad database design. So we can say first normal form is the basic requirement, and to follow this should become your default nature while creating tables to store data. Also, it is the step 1 to move on to second and third normal form. The first normal form expects you to follow a few simple rules while designing your database, and they are: rule number 1. Each column of your table must be single valued, which means it should not contain multiple values. We will explain this with help of an example later. Let's see the other rules for now. Rule number 2. This is more of a common sense rule. In each column, the values stored must be of the same kind. For example, if you name a column date of birth to save date of births of a set of people, then you cannot or you must not save names of some of them in that column along with date of births of others in that particular column. It should hold only date of birth for all the entries or rows. Rule number 3 expects each column to have a unique name. This is to avoid confusion at the time of retrieving data. If one or more columns have same name, the DBMS system will be left confused. Rule number 4 says that the order in which you store the data in your table doesn't matter. Although all the rules are self-explanatory, still, let's take an example where we will create a table to store student data, which will have student's roll number, their name, and the name of subjects they have opted for. So we will be creating a table with 3 columns. We can obviously have as many columns in our table as we want, but for our example, we only need 3. We will name the columns roll number, name, subject. Let's add some data to our table. Now with data added, our table already satisfies 3 rules out of the 4 rules. As all our column names are unique, we have stored data in the order we want it to, and we have not mixed different types of data in our columns. But out of the 3 different students in our table, 2 have opted for more than one subject, and we have stored the subject names in a single column. But as per first normal form, each column should contain atomic values. Now, how to solve this problem? It's very simple, because all we have to do is break the values into atomic values. By doing so, although few values are getting repeated, but values for subject column is now atomic for each row. Hence, a table is in first normal form.
Okay. So what would we have to do then in our example over here? It's clear that here in our example, this table is not in normal form because we have this, there's one person with two departments. We would have to correct something here. So first off, the employee ID, we have an employee ID here that's not correct. We would have to say that this is 101. And we would need to separate these values. So we would remove this value here. And to have it in the, to verify that it's a first normal form, we would have to add here another record that would be Amit from the city Kolhapur. And the department Cognos. Now, this doesn't solve the fact that we can still have anomalies, but at least we are trying to create or we're getting closer to a structure that eliminates these anomalies. So the problem that we're having here is that we don't have atomic values in that column, okay? So now this would be a table in the first normal form. So the first normal form, like the video said, I would say it's a common sense normal form, meaning that naturally in our design, our tables should have the characteristics where there's a primary key, right? We have atomic values, or we know that we're going to be able to have atomic values. That the names of the fields are unique. And obviously the fields don't have to be in a certain order. But that's kind of like the common sense validation or common sense normalization, which is the first normal form. So like the video said, if your database isn't in the first normal form, you're really in trouble. So the database hasn't been, from its original design, is not well designed. All attributes have to be atomic. All values in a field have to be of the same type. Each column has to have its own name, and the order of the columns and rows doesn't really matter. And there must be a primary key. That's the first normal form, okay? Questions with this one before we jump along to the second normal form, where we're going to start complicating things a bit. No? Okay. Now let's go to the second normal form. Now, a table is going to be in the second normal form. First off, we need to have it in the first normal form. So we need to validate the things we saw on the previous slide and in the video. We need to validate that first. So once it's in first normal form, we need to verify that every attribute that is not a key depends functionally and totally on the primary key. That means that an attribute or a field cannot depend on anything else that is not the primary key. If the dependency is from the primary key and another attribute or any other attribute, then there is, that's what's called a partial dependency. And we can't have that because that generates, that can generate problems and confusion. And so sometimes what we're going to have to do is create what we call a composite key, which means that we're going to have to grab more than one attribute to be a primary key. We're going to have grab more than one attribute to be a primary key. And these are called composite keys. So let's look at a video that has to do with that.
For just $67, you can make as many videos as you want, and you never need to pick up a camera or use any fancy editing software. With Doodly, you drag, you drop, you tweet.
Hey everyone, welcome back to Study Tonight's YouTube channel. I would like to start with an apology for the delay in this video. We received a lot of comments and requests over email for making video for the second and third normal forms, and we want to thank you all for that. It feels good to know that you guys are equally excited and loving the content.
It's
So
very good.
without
Thank you
any
very
further
much for
delay,
creating it.
let's start.
Go ahead.
In this video, we will cover the second normal form of normalization. We will discuss about the criteria required for a table to be in second normal form and why second normal form is so important. For a table to be in second normal form, it must satisfy two conditions. First one, the table should be in the first normal form, and the second one, there should be no partial dependency in the table. We have already covered the first normal form in a previous video, so if you missed that video, we suggest you to go check out that video first. Now the main question is, what is partial dependency? To understand partial dependency, we first need to understand what dependency in a table is. So let's take an example of a student table in which we save student's name, student's registration number, student's branch, and student's address, etc. In this table, student ID is the primary key and is unique for every row. Hence, we can use the student ID to fetch any row from this table. Even for a case where student names are same, if we know the student ID, we can easily fetch the correct row or column of data. Primary key is nothing but a column or at times a group of columns which can uniquely identify each row in the table, or in simple words, all you need is the primary key to fetch any data from the table. For example, I can say give me the branch name of student with ID 10 and I can get it. Similarly, if I ask for name of student ID 10, I will get it. So all I need is student ID and every other column depends on it. This is dependency in table. Now that we know what dependency is, we are in a better state to understand what partial dependency is. So for a simple table like student, a single column, which is student ID, can uniquely identify the complete row or all the others.
Yes, dear professor.
But this is not true all the time. Now let's extend our example to see if more than one column together can act as a primary key or not. Let's create another table for subject. In this table, we have subject ID, which is the primary key for this table, and the subject name. Again, subject ID can be used to get all the information stored in all the other columns. Unfortunately, there is only one other column in this case. Now we have a student table with student information and another table for subjects. During exams, another table score is created to store the marks obtained by every student in the respective subjects. Also, name of the teacher who teaches the subject is saved along with the marks. So in our score table, we will have columns score ID, student ID, subject ID, marks, and teacher name. Let's add some data to this table. As you can see in the score table, we are saving student ID to know which student's marks are these, subject ID to know for which subject the marks are, and the marks and the teacher name. In this table, we can say that the primary key is score ID, but student ID and subject ID together forms a more meaningful primary key for this table, and we can fetch all the information using it. You would ask how? See, if I ask you to get me marks of student with student ID 10, can you get it from this table? No, because you don't know for which subject. And if I give you a subject ID, you don't know for which student. Hence, we need student ID and subject ID together to uniquely identify any row of data because we have a many to many relationship here. When I say that we have a many to many relationship here, I mean a student can appear for any number of subjects test. Also, a subject can be opted by any number of students. Now, if you look at the score table, we have a column named teacher, which is only dependent on the subject. For Java, it is Java teacher. For C++, it is C++ teacher, and so on. Now, as we just discussed, our primary key here is a composition of two columns, which is student ID and subject ID. where the teacher's name only depends on subject. It has nothing to do with student ID. This is partial dependency. And for a table to be in second normal form, this should not exist. Now the question arises how to remove this. There can be many different solutions for this, but our objective is to remove teacher's name from score table. We can do this in many different possible ways. One of the ways is to move teacher name to the subject table, where it fits appropriately along with the subject names. We can also add the respective teacher's name. Or we can also create another table for teacher and use the teacher's ID wherever we want. So this is the second normal form. In this video, we have tried to explain the second normal form using a very simple example. We advise you to practice because we think that as you will practice more, you will learn more about how second normal form is actually very useful in practical applications. Also, we advise you to start using auto increment primary keys because that will make your life a lot simpler. Hey everyone, hope you enjoyed this video and we promise we're coming up with the third normal form very soon. Apart from that, we're also working on an entrepreneurship tutorial or course in Hindi, especially for the Indian students that we have. And apart from that, we're also working on a very unique programming tutorial which will include a 7-day challenge to learn something new, like Java or maybe Python. So we will start with Unity Engine to develop games in 2D and 3D. So stay tuned. If you haven't subscribed to the Study Tonight channel, it's time you do.
Okay, so the video explained or doesn't attempt to explain the second normal form. And basically, again, what we want there is that we need all the attributes to depend completely on the primary key. And that means that we might need to create a composite primary key. That means that we're going to grab more than one attribute and combine them to make a primary key that's comprised of two or more attributes. This is called a composite primary key. And we want to eliminate partial dependencies. And the partial dependencies is where I have an attribute that depends on another attribute, but this is not related to the primary keys. So in that case, usually what we do there is we do a separation of tables. By the way, we're doing all of this because, again, if we were to have, if we take a problem like the ones we had worked on up to this point, where there's a problem definition and from there we create the entities and go through the whole process, in most cases, these things are going to be resolved because of the way we're creating the relational model. We just need to validate them. But as we're going to see, there's going to be other situations where we're going to be working the other way around. So instead of me giving you a problem for a company called Sosa Corp, I'm going to directly tell you, these are the reports I need to generate. This is the end result. And you're going to be looking at the end result. And from that end result, which could be a report, an invoice, a query, whatever, from that, you're going to have to create a database. This sometimes happens when you've got these situations where there's these huge tables or databases that were created with other structures or methodologies, and you need to maybe recreate it based on the information you have or the reports that are being generated by some system. And in that case, you might have these very large tables that you're going to have to separate and validate. And so the second normal form is very important because, again, all of the attributes must depend on the primary key completely, totally. And we can't have any attributes that depend on another attribute that is not a primary key. And in those cases, we separate we need to separate the tables. Okay, so that's the second normal form, okay? And the second normal form talks about these functional dependencies and partial dependencies. And these are what we're trying to eliminate from the structure of our tables. Now, the third normal form has to do with something that's called a transitive dependencies. And this is where we have no dependencies between attributes that are not key. So we've got attributes that aren't key attributes, and these are related somehow to each other, similar to what we saw in the last table. We want to eliminate those. These are called transitive dependencies, or dependencies that only occur for a certain specific situation. And obviously, to go to the third normal form or the third normalization, we have to have passed the previous ones. We have to be in second normal form to be able to go to the third one. So let's watch a video about that. Switch over.
Good grammar and spelling are important, but if you want to write essays that inspire.
Hello friends, and welcome to Study Tonight's YouTube channel. In this video, we will talk about the third normal form. If you're following our normalization videos from starting, then you must have already seen the videos for the first and the second normal forms. If not, I suggest you to watch those videos before starting with this one. In the last video, we learned about the second normal form and even normalized our score table into the second normal form. For a quick recap, we had three tables: student, subject, and score. Following were the primary keys. Score table had teacher's name, which was only dependent on subject, so we moved it to the subject table. Hence, now the score table is normalized to the second normal form. But we missed to add some information in the score table in our last video. We need to save exam name and total marks also in the score table. So should we just add them in the score table? Let's do it. So here is our updated score table. So coming back to the third normal form, for a table or a relationship to be in third normal form, it must be in the second normal form and it should not have transitive dependency. Remember partial dependency? This time it's transitive dependency. They're different. To understand what partial dependency is once and for all, watch our video for the second normal form. So what is transitive dependency? With exam name and total marks fields, our score table now looks like this. Primary key for our score table is a composite key, which means it's made up of two attributes or columns, student ID plus subject ID. As we can see, our new column exam name depends on student and subject. For example, a mechanical engineering student will have workshop exam, but a computer science student won't. And for some subjects, you have practical exams, and for some you don't. So we can say that exam name depends on student and subject both. And a second new column, total marks. Does it depend on student or subject or marks or the new column exam name? Well, total marks depends on exam name. You must be thinking how. In our colleges, practical exams are generally of 40 marks or 30 marks, and theory exams are for 70 or 60 marks. Sessionals are of around 40-50 marks. So all in all, total marks changes based on exam. Hence, we can say that total marks depends upon the exam name. Now in our table, we already know that the primary key is student ID plus subject ID, and all other columns or attributes depends on it, except total marks, which depends on exam name. But exam name is not a part of a primary key, right? This is transitive dependency. When there is an attribute in a table which depends on some non-prime attribute and not on the prime attributes. And the solution to this problem is take exam name and total marks and put them in an exam table and use exam ID wherever required. So now our score table is storing more information and it is in the third normal form. Hope you like this video, and I hope that now you understand the third normal form in a better way. Don't forget to share this video with your friends and colleagues, and if you haven't subscribed to our channel yet, please do subscribe to our channel.
Okay. And so, I'm sorry. And so for the third normal form, what we have in the third normal form is that we want to eliminate transitive dependencies. And these are dependencies that occur between two attributes or or many attributes that are not key attributes, like the example that we have there. So we have a table it's a big mashup of a table with students, courses, grades, and the grades only depend on the course, but the course isn't a primary ID, primary key, I'm sorry. And so in that case, these have to be eliminated. And if you're noticing, how do we eliminate them? We usually eliminate them by creating new tables or separating the tables. And that's usually going to be the practice. By the way, there's many more many more normal forms. So we're just going to cover up to the third normal form, but there's many more normal forms. 7, 8. There's a bunch of them that go into very much more detail rather with regards to the analysis and validation of the tables. If at some point you take a complete database course in your graduate program, or you maybe even may even have the opportunity to take it as an elective if you want, you believe me, you'll go into detail about these. But for the purpose of this course, I just need you to understand the concept of normalization and at least these three forms of normalization that have to do with the basic form, which is the first normal form, that all databases have to have it. The second normal form, which has to do with partial dependencies and composite keys, and the third normal form that has to do with eliminating transitive dependencies. That's what I need you guys to know and understand. And we're going to be doing a bunch of exercises. And so there's the three normalization oaths, or how are we going to remember this? So the first normalization is that we've got 4 rules, and the table must have a key, and all shall be dependent on the key. That's a functional dependency. So the first normal form says that there are 4 rules. Remember, the 4 rules are that all values have to be atomic. All of the values have to be of the same data type. The attributes or fields have to have unique and different names, and the columns and the information, the data can be organized, the fields in any way. And there must be a key. So the first oath is the table must have a key, and all shall be dependent on that key. The second normal form says we have to be in the first normal form, first off, and the table must have a key, and all shall be dependent on the whole key. Okay, what's the difference with the first one? In the first one, we just have a primary key, but there might be attributes that don't depend completely on that key. They depend on that key and something else. In the second normal form, all of the attributes must depend on the whole primary key and only that. And that means that there's a functional dependency and there are no partial dependencies. I'm sorry. Lastly, in the third normal form, it means that we're in the second normal form. The table must have a key. All shall be dependent on the whole key and nothing but the whole key. That means that there's a key. Everything depends on the whole key. And besides that, there isn't an attribute that depends on something else that isn't that. And nothing but the whole key. So there's a functional dependency, there's no partial dependencies, and there's no transitive dependencies. Those are basically the three rules that we're gonna follow. Okay. And just to kind of give a summary of the keys, because right now, up to this point, we've only talked about a primary key, which is this key that identifies the it's a group of attributes that identify uniquely a set of records in the values in a table. There's going to be different versions of keys from now on. And we're also going to do some exercises with regards to that. The first concept that we're going to talk about is a super key. A super key is a set of attributes for which the values are guaranteed to be unique for all possible combinations of the records in the table. And so that means that if I have a table, there are 2 to the n possible super keys, which are basically all of the combinations of the different attributes that I can have. A candidate key is a minimal super key, meaning that it's the smallest super key that I can have. Now, what are we talking about when we talk about super keys, by the way? If we go back to this one, so there's different super keys that we can have here. And I'm just going to mark them here. One of them is this whole mashup of these 4 together is a super key. Why? Because if I take all of the attributes together and make them one big key, then I can access any of the information here. The others are different combinations of these. So I could grab these 3, and they're also a super key. I could grab these 3 here. This could also be one. And so on and so forth. So if I have 4, if I've got 4 attributes, then I'm going to have 2 to the 4, in this case, 16 possible combinations that I can use as super keys. Now, obviously, a primary key that has all of the attributes is not going to be practical. And so of all of the possible keys that I can have, oops, I open this again.
Actívate, desvanece tus canas fácilmente.
I need that. Definitely need one of those. Why isn't this closing up? There we go. A candidate key is going to be a minimal super key. It's going to be the smallest one that I can create from all of the possible combinations. From that, there can be many candidate keys. I'm going to identify a primary key, which is the one I'm going to use in the end in the database. It's of the different candidate keys that I have, I'm going to choose one of them, which is a primary key. In the examples we've seen up to this point, it's been very obvious that there's one primary key, but there might be other situations of tables where it's not that obvious and we need to validate this. An alternate key is any other candidate key that I can have that can also be used as a primary key. A composite key or compound key is going to be a primary key that has more than one attribute. 2, 3, or maybe more that comprise that. Not necessarily all primary keys are going to have just one attribute. A foreign key, if I have 2 tables, is a key that is a primary key of another table. So remember when we had these relationships where in the relational diagram where we had employees and departments, and so because of the relationship, we added the key to the other table. And so these are going to be keys that link up one table from another. So I may have an attribute in one table that's referencing a primary key from another table, and that's called a foreign key. And so this kind of wraps up the theory part of normalization. And the next thing we're going to do is that, and we're going to do that next class, is we're going to hit the ground running with some examples. And I'm going to be working here some examples in class. We're also going to record those. And you guys are going to do some exercises so you can practice.